So we're just going to show the solutions to this week's workshop problems. First one is what is the error in this solution? Um, the error is occurs right here, where we change the integral from an integral in x into integral in u without changing the bounds of the integral. Now, why is that an error? Well, one of the points that we made in the lecture videos is that when you change an integral from one variable to another, you have to change the limits of integration into that variable. So in this case, since u equals x squared plus 3, we would have to change the 1 and the 5. We'd have to get u of 1 is equal to 1 squared plus 3 is 4, and u of 5 is 5 squared plus 3 is 28. So we'd have to use an integral from 4 to 28 when we write the integral in u. Now, why is that wrong? The reason it's wrong is because of something, that you all know about, and that thing is this symbol here, the equal sign. When you put two things on either side of an equal sign, they should actually be equal to each other. And the problem with the solution that Sandy did is that these two things are not equal to each other. In fact, I've put up precisely what these values are. So Sandy claimed that these two things were equal to each other, but in reality, if I calculate the first one, I get the solution that's the end of the problem, because I did say that that was the correct solution, and that equals about 46.721. And if instead, go back up here, Sandy asserts that that original integral is equal to this integral in u, but when I calculate that integral, I get 3.39, and clearly those two things are not equal. Now, I'm not saying that that's the best way to do it. I'm not saying you want to take out a calculator and find the decimal value of these two integrals, but you should recognize that when you don't change the limits of integration, when you change the variable, you're making a mistake. By the way, there was another mistake in here, which is that I forgot to put the 3/2 exponent in that spot, but that was actually just a typo. That wasn't really part of the problem. But congratulations if you did recognize that. I didn't recognize it until I was just writing out these solutions. Okay. So, question number 2. Let's use u substitution to convert each of these integrals in x into an integral in u. The point here that's being made is really the same. In the first case is really the same one, that you have to change the limits of integration. We can say that u equals x cubed plus 2. We're given that fact. Therefore, du equals 3x squared dx. So that means that 1/3 du is equal to x squared dx. We have to replace an x squared dx along with a cosine of x cubed plus 2. So I is going to equal the integral of 1/3 cosine of u du. And we also have to change the limits of integration, of course. So since u equals x cubed plus 2, that means u of negative 2 is equal to negative 8 plus 2, or 6, and u of 4 is equal to 4 cubed, which is 64, plus 2, which is 66. I did not mean to put sorry, this, by the way, is actually negative 6. I did not mean to put 3 6's in one integral. It just worked out that way by accident. Okay, so for part B, we're given that the integral I, that you can see there, should come out to some integral that has e squared and e to the 5th as its limits of integration. So how are we actually going to do that? Well, so the way we'll do that is we want to choose u such that u of 4 is equal to e squared and u of 10 is equal to e to the 5th. A function that will do that very nicely is u equals e to the x over 2, because then we plug in 4 and we get e squared, we plug in 10 and we get e to the 5th. In that case, du is equal to 1 half e to the x over 2. So just get rid of this. So that means that 2 du is equal to e to the x over 2. We can therefore see that I is equal to, I need to replace an e to the x over 2 dx, which I can replace with 2 du. So this is going to be 2 square root of 1 plus, I need to replace an e to the x. Let's just observe that e to the x is equal to e to the x over 2 to the 2. So that means that it's equal to u squared. So this is going to be 2u squared du, like that. So there's that answer, and there's that answer. Okay, let's move along. Here we're given a picture of a region between two curves and some integrals that are wrong. So first of all, let's look at A. So why is A wrong? A is wrong because in order to find the area between two curves, we need to intersect top minus bottom. And since we can see is that F is the blue dotted line and G is the red solid line, this top minus bottom paradigm is only true for the interval from -1 up to 2. It's not valid on the interval 2 to 4. So the answer is that F is not the top function for the entire interval of integration. Now, in the case of B, really we have the same problem. Here, what I've done is I've asserted that for the entire region, that g is the top function. But as you can see, g is only the top function for this part and not for this part. So g is not the top function on the interval -1, 2. So that's the error in the case of B. Now, if we were to write the correct integral, we simply have to break this up into two integrals and make sure that we always have top minus bottom. So the area is actually going to equal the integral from -1 up to 2. We're going from this line up to this one, and that's going to be top minus bottom, so that's going to be f of x minus g of x dx, and then plus, we're going to go now from 2 up to 4. That gives us the integral from 2 to 4 of g is now the top function, so g of x minus f of x dx. Oh, and by the way, somebody else pointed out during one of the problem-solving sessions that you should attend that I'm missing a dx there, and that is true. Kudos if you found that, but that again was actually just a typo in the workshop. We'll try to avoid having typos in the future, but it's always very hard. So anyway, this is the answer to problem 3. Okay, so the integral, excuse me. All right, so the integral -1 to 2 of x to the 4th plus 3 minus the square root of x plus 4 gives the area of a region between two curves. Describe the region. The thing you have to recognize is that if I gave you some region like this, if I said, here's f of x and here's g of x and here are two vertical lines, you would very easily be able to form the integral that gave me the area between these curves. But what I'm asking you to do instead is to reverse the process and come up with what the region looks like that would be the answer to the question. So let's draw this again. Draw the axes again. So the first one we can see is that this is going to be a top function and this is going to be a bottom function. So x to the fourth plus 3 looks like this. It's not technically a parabola. I'll draw it a little bit higher, actually. It's not technically a parabola. Not every u-shaped function is a parabola. This is it's a quartic function, and it's a little bit flatter on the bottom than a parabola. And then square root of x plus 4, this is just the square root function shifted 4 units to the left, so that's going to be this. And you can see, either using a graphing calculator or Desmos, or just what you know about the values of these functions, that these two curves do not intersect each other at all. Now we can see that since the limits of integration are -1 and 2, what we have is we have a vertical line at -1 on that side, and we have on this side, I'm not really drawing it to scale, we have a vertical line at -2. So this is, sorry, at +2. So this is x equals 2, this is x equals -1, and what we have finally is this region between them. So if you want to answer the question, because of course the whole point is to be able to draw this and then describe it in words, what I would do is write this. I would say it's a region that is bounded on top by y equals x to the fourth plus 3, on the bottom by y equals the square root of x plus 4, on the left by x equals -1, and on the right by x equals 2. So that's the answer to that question. It's difficult. I know many of you are very good at setting up the math problem and solving it, but having to actually describe in words what you're doing is sometimes kind of a humbling experience. So, all right, let's go on to problem 5. Okay, problem 5. So this one is it's not difficult, but somehow looks harder. So the thing is, if you take a look at just, let's say, this part of the integral, this part of the expression, it should be fairly clear that what we're doing is we're just integrating the line y equals 1/3 x on the interval 0 to 3, and that's what I've shown in the blue region here. In other words, this is the integral of y equals 1/3 x going from x equals 0 up to x equals 3. And that just gives you the area under a curve. This is something that you've known since roughly the end of Calc 1, is that that's what an area under the curve integral looks like. Now, let's make it clear that that's a plus sign. Then I'm giving you just a different line, which is the line y equals 4 minus x, and the y equals 4 minus x, and we're integrating that on the interval 3 to 4, which happens to be next to the interval from 0 to 3. So what we have here is, in between these two regions, the blue one and the orange one, both of which really are clearly described by these integrals, the entire region is just the combination of the two. I'll just draw a red dotted line around that. So we have this triangular region. What you're being asked to now is to set up a dy integral that gives you the area of the same region. Well, we know that dx integrals are top minus bottom, and dy integrals are right minus left. So what you have to do is recognize that now this is the right function. In other words, the green curve, the green line rather, is the right function, and the purple line is the left function. So the first thing we have to do is convert, sorry, that was the first thing we had to do. So the second thing we have to do actually is convert the two equations for the line into x. So if y equals 1/3 x, then that's equivalent to saying x equals 3y. And if y equals 4 minus x, that's equivalent to saying that x equals 4 minus y. Again, just solve for x in terms of y. So we now have these two curves, x equals 4 minus y and x equals 3y. We have the right and left curves now written in the form x as a function of y instead of y as a function of x. So there's just one more, actually I'll just write out the area integral and then we'll put in the last piece in a second. So we can write that the area is equal to the integral of right minus left, which is going to be 4 minus y minus 3y dy. So this is going to be, that's the right side of that colored region, the triangular region, and this is the left side. And now we just have to put in the limits of integration. Limits of integration come from looking at the lowest possible value of y, because we're doing it in the y direction. So instead of looking for two vertical lines on the left side of on the left and right side of the region, we're looking for two horizontal lines on the bottom and top. I'm putting those lines in. You simply need to know what that point of intersection is. If you plug the number 3 into either of the original equations, y equals 1/3 times 3 is 1, and y equals 4 minus 3 is also 1. So this is clearly y equals 1. In fact, this point of intersection is the point 3, 1, like that. So we're integrating from 0 up to 1, and that's the answer. Okay, let's do another one. So following integral gives the area of a region using a dy integral. Let's set up an expression using one or more dx integrals to give the area of the same region. So what you have here now is you're given the right minus left integral, and you have to convert it into a top and bottom integral. Now, first thing you want to do, of course, is you want to convert these expressions. What I have here is I have the two curves x equals 4 minus 2y and x equals y minus 2, and I want to convert them into y as a function of x, which I've already done. Now, the complication in this problem is that what you can see is that we have the area under two curves, but even though I was able to set up the area of this region as a single integral in the y direction, what I'm actually going to get in the x direction is the area under two separate curves. In other words, I have the area under the purple curve. This will actually, let me put these next to their respective curves. So I have the orange area is the area under the green curve, and the blue area is the area under the purple curve. So now I can go and convert these back to the familiar direction. It feels a little bit like whiplash here. You're going from the complicated to the easy, because you just went from the easy to the complicated before. We now see that we're trying to integrate from a vertical boundary of x equals -2 up to a vertical boundary of x equals 0, and then onward to this vertical boundary of x equals 4. Where did I get those values? Well, I just set y. I can find the x-intercepts just by setting y equal to 0 and solving the equation. So we can see the purple line intersects the x-axis at -2, and the green line intersects at 4. So we're just going to do the sum of two areas under curves. So this becomes the integral from -2 to 0 of the purple line written y as a function of x. So that's going to be x plus 2 dx, and then plus the integral from 0 to 4 of the green line, which is 2 minus 1/2 x dx. So there we go. And I'll just mark in here what's what. This is the blue region, and this is the orange region, like that. Okay. Now, let's see. This is certainly the hardest problem in the workshop. So you're given the area of the region shown using a dx integral, and you want to set up an expression with dy integrals to represent the area of the same region. So let's see what's going on here. Certainly, what this integral gives is the area under the natural log curve. I've drawn in the natural log curve using a green line, y equals ln x, and uh, it's the integral. It's the area under the natural log curve on the interval 2 to 3. So in other words, between the two vertical lines x equals 2 and x equals 3. We want to convert this into a dy integral, which means what we're looking to do is add up rectangles that look sort of like this and whose height is dy, where the thickness of the rectangle is dy and its width is given by right minus left. Now here's the thing that you have to recognize when you do this. This is the real complication here. And this is how you figure out what is right minus left in one of these drawings. Draw a horizontal line through the region and see where it intersects the boundaries of the region. What we'll see is that it intersects there and there. That should tell you what the left and right boundaries are. So it certainly looks like the left boundary is going to be the line x equals 2, and the right boundary is going to be the line x equals 3. The only complication here is that x equals 2 is not always the left boundary. It's certainly the case that x equals 3 is always the right boundary for this yellow region. But if I were to draw a horizontal line up here, let me draw it a little bit higher. If I were to draw a horizontal line up here, what you can now see is that it's the green curve that forms the left boundary. So depending on where we are, it might be the line y equals ln x. Now, since we're going to do the integral in the y direction, we actually can't use the equation y equals ln x because we write x as a function of y. So let's set this up. So let's first of all find what the green curve is. So y equals ln x. Solving x for y, it gives us e to the y equals e to the ln x. So e to the y equals x, or x equals e to the y. So this curve can also be written as x equals e to the y. Next, what we need to do is figure out exactly where the definition of the left boundary changes. And the answer is it changes at that point. Below this red dot, the left boundary of the yellow region is the vertical line x equals 2, but above this red dot, it's going to be this green curve. So we need to figure out what this point is. We can do that by taking y equals ln x and take y equals ln x and just plug it in and plug in the number 2. So this is going to be 2 comma ln 2. And we also are going to need to know what the highest part of the region is, because we're going to need that for the limits of integration as well. That's going to be determined by this point, which is 3 ln 3. Okay, so let's form the integral for the area. That's going to be area is equal to the integral. We need the lowest possible y value for the region, which is down here. That's going to be y equals 0. Keep the colors consistent. It's going to be y equals 0, and then it goes up to this number here. This is going to be ln 2. In other words, that's, just write in the lines. This is y equals 0. This line is y equals ln 2. And this line up here is y equals ln 3. We're proceeding upward as we integrate in the y direction, so we want to know what important boundaries we encounter. So going up to this line, 0 to ln 2, we can see that right minus left is just going to be 3 minus 2. barely need an integral to do that, but we do want to set up the integral correctly. So we're writing that as y minus, as right minus left. Now, for here, we're going to go from, we need to go from this line up to this one. So I'm going to integrate from ln2 up to ln3. And now I'm going to once again form the integral of right minus left. So that's going to be 3. That's the right boundary. And do we write in ln x? No, because we need this in the form of, we need this in terms of y, so we're going to use this form of the function, e to the y dy. And I'll just write in here that this is right, and this is left, and this is right, and this is left. It's important to understand exactly where all of these numbers come from. In other words, why this is the right boundary and this is the left one, 3 and 2, and then why it switches from 3 to a right and left boundary of 3 and e to the y, and also how these lines figure in and where the definition of the function switches at where the definition of what the left boundary is switches at ln2, and that's why you have to break up the integral into two intervals, 0 to ln2 and ln2 to ln3. So there's the answer, and we'll see you next week.